Our topic for today is about evaluating limits using Squeeze Theorem. Now, you might be wondering why there is a picture attached in the presentation, uh, which is a sandwich. Okay, and the reason for that will be explained once we discuss the theorem itself. So let's discuss the theorem. Okay, the theorem says that if f of x is less than or equal to g of x, and g of x is less than or equal to h of x when x is near at c, except possibly at c, and the limit of f of x as x approaches c is equal to the limit of h of x as x approaches c, which is equal to L, then the limit of g of x as x approaches c is equal to L as well. So let's analyze the given theorem. Okay, the given theorem, which is called Squeeze Theorem. Now, as you can see here, g of x is in between the two functions f of x and h of x. Or the g of x here is being squeezed by the two functions. That's why it's called Squeeze Theorem. Or in other words, the function g is sandwiched by the two functions h and f of x. Right? That's why theorem number one is also called as sandwich theorem. And this explains why there is a sandwich picture in the given presentation for you to easily remember. Okay, and let's discuss theorem number one. So here it says here that whenever we are finding or solving for the limit of g of x, and if it's quite hard to find the limit or of the function g of x, then we can find two functions which are greater than the given g of x or less than the given function g of x, which is f of x. And then if we get the limit of these two functions f and h, as long as their limits are equal, let's say L, then we can find the limit of the function g of x. And it turns out that the limit of g of x is also equal to L. So if the limit, let me write it down. So let's say we have g of x is less than or equal to h of x, okay, but greater than or equal to f of x. So again, as I mentioned earlier, if ever it's quite hard to find the limit of g of x as x approaches c, let's say, okay, c is a real number here, and there is another way to solve for the limit of g of x by finding two functions which are greater than g, okay, where the function values are greater than g of x, and the other function is less than the value of g of x. So this becomes limit f of x as x approaches c, and we can find also the limit of this as x approaches c. And if the limit of this right-hand side is L, okay, which is greater than or equal to, we don't know the exact limit of g of x, but we knew that the limit is less than or equal to L, all right? And also the limit of g of x as x approaches c is greater than or equal to the limit of f of x as x approaches c, which is L. Then since these two values are equal, then we are so sure that the limit of the function g of x, which is quite hard to be evaluated or to be found out, is already equal to L. Since the limit of g of x must be between two L's, but L is equal to L, so therefore, okay, the limit of g of x is equal to L. All right. So how do we illustrate that using a graph? Now, in using a graph, let me change the color. Let's say we have an coordinate plane here. All right. Now let's say h of x is a blue one. Let's say this is a blue one. Okay. So blue. Oops. Okay, the blue one, h of x is the blue one, which means that all the values of x, function values of x, are greater than or above the x-axis, okay? Which is greater than or equal to the function values of g, all right? And also, the function values of f of x, or f, are less than the function values of g and h. So let's say the f is the white one, okay? So let's say the function values of f are less than or below the x-axis. And since the value of g of x, or the function values of g of x are between, okay, between the function values of h and f, so the graph or the points of g could be lying here, somewhere here at the middle, all right, somewhere there. So that's why it's called sandwich, because the function values of g are sandwiched by the function values of h, and this is by f. Or the graph or the function values are sandwiches or squeezed by these two graphs, the h and the f, okay? So the name itself tells us what is the meaning of the theorem itself. All right, so being sandwich, which means that if the limit of a certain function at as x approaches c is equal to L, and the other one, which is f, is equal to L, therefore the limit of g, okay, which is sandwiched by f and g, is also equal to L. All right, that's what it means here. Okay, so the theorem, Squeeze theorem, is actually very useful when when evaluating a very, let's say, complex, okay, complex function, which quite hard to be evaluated by its, okay, limits, or finding its limits. All right, so let's apply the theorem. Okay, so let's have problem number one, the limit of sine x over x as x approaches infinity. Now here, since we're talking about trigonometric function, sine x, then we can use the graph or the behavior of the graph of the sine x function. Okay, so before we apply the squeeze theorem or the sandwich theorem, now let's try analyzing the graph of sine x. All right, so let's sketch the graph of sine x. Okay, and let's use color red. All right, now we know that the graph of sine x is, okay, it intersects the origin, and it goes up, down, and up, and down and up. And it is continuous, okay, from left to right and right to left. And of course, this go this way. And we know that the maximum value of sine x is equal to 1, and the minimum value is equal to -1. All right, so we can say, or we can write, sine x is less than or equal to 1, but greater than or equal to -1. Okay, so as x approaches infinity, now there is no specific value that this graph is approaching to, because it keeps on rising up to 1 and falling up to 1 and go up again and down again, up again and down again. So the limit is quite hard to be identified or determined. All right. However, if we're going to analyze the given problem or the given function sine x over x, now let's analyze it first. So in this case, we know that the function values are ranging from -1 to 1, correct? And since x is infinity, approaching infinity, therefore, the value of x here is infinite, all right? It approaches infinity as well. Now, whatever the numerator here from -1 to 1, since x is getting bigger and bigger, a very large number, all right? And we know that when a fraction has a very big denominator and the numerator is constant, okay? And when the denominator is getting bigger while the numerator is constant, then its value or the fraction, okay, the value of the fraction or the expression is approaching 0. So therefore, whatever the value of the numerator here, since it's just so small from -1 to 1, while the denominator is approaching infinity, therefore the fraction is equal to 0, or I mean, it approaches 0. That's why the limit, okay, the limit of sine x over x as x approaches infinity is equal to 0. Okay, so that's what our answer is all about by analyzing the values, specific values of the numerator and denominator. Okay, all right. So in this case, let's apply the squeeze theorem on how we're going to get 0. Okay, the squeeze theorem will give us a very good way of showing the solution. Okay, so let me just change the color. Okay, and let me just erase. Okay, erase. But we know that the answer is 0, so let's check that later. Okay, so using squeeze theorem, now let's, okay, this is our solution. And we know that sine x is less than or equal to 1, but greater than or equal to -1. Okay, and our main aim here is that we want to find the expression, the given function here in the given problem in this expression, okay, or inequality, compound inequality. So how do we get sine x over x in this inequality? Then for us to get sine x over x, then we need to divide all of the terms here in the inequality by x, all right? Okay, since we have x here. So we already found the middle term, okay, which is sine x over x, which is equal to or the same as the given function in given problem, okay? So here, for us to find the limit of the sine x over x, then as x approaches infinity, then we can take the limit on all of the terms in the given inequality. So we could have the limit of -1 over x as x approaches infinity is less than or equal to the limit of sine x over x as x approaches infinity is less than or equal to the limit of 1 over x as x approaches infinity. So since, again, for me, it's quite hard to find the limit of this middle term. So I might work on the left-hand side and the right-hand side of the expression or the inequality. So what is the limit of -1 over x as x approaches infinity? Since, again, x is increasing without bound, all right, it becomes bigger and bigger and bigger. So -1 over infinity is equal to 0. As we said, as the denominator goes bigger and bigger and approaches infinity, while the numerator is constant, then the value becomes 0, right? Or it approaches 0. So here, the limit sine x over x, since I don't know what the value of this expression or function is, so I'm just going to copy the expression, okay? And also, let's take the limit of the right-hand side of the inequality. What is the limit of 1 over x as x approaches infinity? So same thing with the left-hand side. As the value of x increases, the value of the fraction 1 over x is decreasing, right? And it approaches 0. So here, we can observe that the limit of sine x over x as x approaches infinity is less than 0 and or but greater than or equal to 0. So which means that there's only one value that the limit of sine x over x as x approaches infinity will be equal to, or will be approaching to. And that is the limit of sine x over x as x approaches infinity is equal to 0. So our answer was correct that it's limit is equal to 0. Okay, and with the use of squeeze theorem, the sine x over x was squeezed by the values 1 and -1, and by when it comes to the limit, by the limits of 1 over x and -1 over x. So this is how we apply the squeeze theorem or the sandwich theorem. All right, and but of course, with a good background of trigonometry, especially the graphs of trigonometric functions, then it would be easier for you to identify the limits. Okay, now let's move on to example number 2, and I hope you understood how we apply theorem or squeeze theorem in solving limits of some functions which are quite hard to solve or to evaluate. All right, and the squeeze theorem is not just applicable to functions which involve uh, trigonometric functions. Okay, it can also be used with other types of functions given. Okay, so in number 2, the limit of 2 minus cosine x over all over x plus 3 as x approaches infinity. Now, so with this, it's quite hard to get the limit when we talk about the second term, which is the cosine x. Okay, the numerator of the given fraction. So I will start from the cosine x term in the numerator. So let me change the color, yellow. Okay, so solution. So I know that cosine x, okay, has a maximum value of 1 and a minimum value of -1. That's the range of the cosine function, right? From -1 to +1. Okay, and here, I want to express this inequality, compound inequality to 2 minus cosine x. So for me to do that, I will subtract or multiply all of the terms by -1. So this becomes 1. Okay, since we're multiplying negatives, of course, the sign or the inequality symbols will be changed to its opposite. So this becomes negative cosine x greater than or equal to -1. Or this could also be written as -1 less than or equal to negative cosine x less than or equal to 1, right? So by just rewriting the values, you can deal with this if you want, but I want to deal with this for me to use the usual, I mean the original orientation of the -1 to 1. Okay, but it doesn't really matter whether you work on this or in this one. Okay, so let's continue. And again, there is 2. Okay, so the expression is 2 minus cosine x. Therefore, for me to express this negative cosine x by 2 minus cosine x, I need to add 2 both sides. So 2 minus 1 less than or equal to 2 minus cosine x less than or equal to 2 plus 1. And this is equal to 1. All right, 2 minus cosine x less than or equal to 3. Okay, so we have already found or expressed the numerator, which is 2 minus cosine x. And what we need to have here is the denominator x plus 3. And for us to totally express this middle term, okay, of the compound inequality to be similar to this, then we can divide, okay, this inequality by x plus 3. So x plus 3. Oh, can't be seen. So let's just put it here. So we have 1 less than or equal to, okay, 2 minus cosine x less than or equal to 3. Divide this by x plus 3. Divide this x plus 3. Divide this x plus 3. Oh, sorry. Okay, so we have already expressed, okay, the middle term of the inequality in terms of the given problem. So what we need to do is to determine or evaluate their limits. All right, so I will get the limit of the left-hand side term, which is 1 over x plus 3, as x approaches what? Infinity, is less than or equal to the limit of 2 minus cosine x all over x plus 3 as x approaches infinity, less than or equal to the limit of 3 over x plus 3 as x approaches infinity. Okay, so we now take the limits on all of the terms if it's possible. But for me, I'd better work on the left and the right hand sides, okay? And if ever the limits of both sides are equal, therefore, that's also the limit of the middle term. So here, as x approaches infinity, the denominator is getting bigger and bigger until it approaches infinity. So that's 1 over infinity, right? Over the limit of 2 minus cosine x all over x plus 3 as x approaches infinity. Oh no, so I lack space. So limit 3 x plus, oh, sorry. So let me just erase it. So here is x plus 3. Oh, it's not x plus 3. It's supposed to be infinity since the value of x approaches infinity. So infinity plus 3 is infinity. All right, so 1 over infinity, same thing. The denominator is so big, okay, where the numerator is 1. Therefore, this approaches 0 and less than or equal to the limit of 2 minus cosine x all over x plus 3 as x approaches infinity is less than or equal to. What is 3 over infinity? That's 0. All right, so since the left-hand side and the right-hand side are already equal, okay, so we are so sure that the limit of 2 minus cosine x is equal to 0, okay? So the answer here is 0. All right, and I hope we got the same answer, and I hope you got the solution correctly. Okay, and let's move on to the next example. Okay, so let's work on problem number 3. So that's limit of x squared times sine of 1 over x as x approaches 0. So how do we solve this? The expression x squared times sine of 1 over x is quite complicated, okay, as we deal with other functions before. So what we can do is we can use Squeeze theorem here. Okay, so let's just work on start with the given trigonometric function, okay, sine of 1 over x. All right, so okay, so let's work on this, which is 0. So here we could say that, okay, and we knew that sine function, all right, has a maximum value of 1 and a minimum value of -1. Okay, so that's the range of sine function. And here, so let's work on this by manipulating the expression, okay? And for us to express this problem in based on the given, so we lack x squared at the middle. So we need to multiply both sides by x squared. So -1 times x squared is x squared negative here, less than or equal to x squared sine of 1 over x is less than or equal to x squared, right? Okay, so I think we're now ready to evaluate its limit as x approaches 0, since we have already expressed the middle term of the inequality similar to the given problem. So let's find the limit, okay? So the limit of -x squared as x approaches 0, copy, less than or equal to the limit of x squared times sine 1 over x as x approaches 0 is less than or equal to the limit of x squared as x approaches 0. right? Okay, so we have already expressed the given compound inequality in terms of limits. So let's evaluate the limits on both sides. So what is the limit of negative x squared as x approaches 0? We know that when there is a negative, we can put it as a coefficient. So that's -1. And what is the limit of x squared as x approaches 0? And of course, it's 0, right? Okay, and less than or equal to the limit of x squared sine of 1 over x as x approaches 0. Okay, and what is the limit of x squared as x approaches 0? Therefore, it's 0, right? So therefore, it's 0 less than or equal to the limit of x squared sine 1 over x as x approaches 0 is less than or equal to 0. So which means that the limit of this expression, x squared sine of 1 over x is equal to 0, since they are, I mean, this function is sandwiched, okay, from 0 to 0. And there's no other value, or there are no other values or value between 0 and 0, which is 0, right? So therefore, the limit of x squared times sine 1 over x as x approaches 0 is equal to 0. So therefore, the answer here is 0. Okay? And again, I hope we got the same answer. So let's work on number 4. Now try to work on this, okay, using Squeeze Theorem. And you can pause the video. Once you're done, you can play the video and let's see if we'll have the same answer. All right? Okay, so I hope you already paused and let's work on this. Here, the problem number 3 is similar to problem number 4. It's just the given function was changed to cosine from sine. All right, but let's check how we're going to work on this. And again, we knew that the range of cosine of 1 over x is from -1 to 1. And for the square or x square, the range is what's that, 0 to positive infinity. So let's work on cosine 1 over x instead, since the range is or has a smaller range from -1 to 1. Unlike in x squared, it's 0 to positive infinity. It's quite hard to work on that kind of range. Okay, so although both of the functions x squared and cosine 1 over x has or have a defined range, all right? But let's work on this. So I know that it's cosine of 1 over x is less than or equal to 1 and greater than or equal to -1. Okay, based on the property of the range of the cosine function. Okay, so let's work on this again. We need to express the middle term or expression in terms of the given problem. So we lack x squared, so we can multiply both sides or all of the terms by x squared. So x squared cosine of 1 over x squared. Okay, let's take the limits. So the limit of -x squared as x approaches 0 is less than or equal to the limit of x squared times cosine 1 over x as x approaches 0 is less than or equal to the limit of x squared as x approaches 0 as well. Okay, so let's take the limits on both sides or on all of the terms. So what is the limit of -x squared as x approaches 0? The limit of that is 0. Okay, and copy, since we can't identify the limit of x squared cosine 1 over x as of this moment. Okay, and less than or equal to, what is the limit of x squared as x approaches 0? 0 also. So since the given limit, okay, of x squared cosine 1 over x as x approaches 0 is sandwiched or squeezed between 0 and 0. Therefore, the limit of x squared cosine 1 over x as x approaches 0 is equal to 0. Therefore, the value here is 0. All right? And I hope we got the same answer. Okay. And let's work on another problem. That's problem number 5. So, how do we work on this? Okay, same thing. Let's try dealing with trigonometric functions. Okay, again, if you want to work on this, try to pause the video and try to work by yourself. Okay, and once you're done, you can play the video to check whether we got the same solution and the same answer. Okay, so let's work on cosine squared 2x. All right, but we know that, let's work on cosine. Let's start with cosine. Cosine 2x is less than or equal to 1, but greater than or equal to -1. Okay, and how did we get that? That's the property of the trigonometric function cosine, right? Okay, and since the given here is square, okay, so we can take the square on both sides. All right, so let's take the square on all the sides. So here, this becomes cosine square 2x is less than or equal to 1. Why 1? Because 1 square is 1. And here, -1 square is 1, right? So it's just equal to 1. So it's just the same as this. But in between of these numbers, -1 and 1, there are numbers which are lesser than 1, and numbers which are greater than -1, like 1 half, -1/4, okay, 1/2, 1/4. So the minimum value of cosine square of 2x is 0, okay? All right, because in between -1, there is 0, correct? And the square of all the negative numbers here are all positives, and here are all positives, while the square of 0 is 0. So therefore, the minimum value of cosine square of 2x is 0. Okay, so cosine square of 2x is now greater than or equal to 0, but less than or equal to 1. All right, so this is now our new range. Okay, and we already got the numerator, so we need to divide all the terms by 3 minus 2x to express the middle term in terms of the given problem. So 3 minus 2x all over 3 minus 2x and over 3 minus 2x. Okay, so here, let's simplify if we can. So 0 over 3 minus 2x is 0. All right, and cosine square of 2x over 3 minus 2x. For now, we can't simplify this yet. And this one, we can't simplify this yet because it's already simplified, right? Okay, so what's next thing to do? Since we have already expressed the middle term in terms of the given problem, now let's take the limit, okay? So let's take the limit of all the terms. So that's the limit of 0 as x approaches 0 is less than or equal to the limit of cosine square 2x over 3 minus 2x as x approaches 0, this is 0, is less than the limit of 1 over 3 minus 2x as x approaches 0, right? Okay, so here, 3 minus 2x as x approaches 0. Okay, good. So here, the limit of 0 as x approaches 0 is equal to 0. Okay, and let's copy. cosine square of 2x over 3 minus 2x as x approaches 0 less than or equal to the limit of 1 over 3 minus 2x as x approaches 0 is equal to what? This is 1/3, right? Because the limit of this is 1/3, right? Since the limit on the left side is 0 and on the other side is 1/3, therefore, the limit of this expression or given function does not exist. Oh, we really don't know yet if it doesn't exist, okay? But for now, we cannot find the limit of cosine 2x over 3 minus 2x yet, okay? So let's take this, let's make this pending. Oh, okay, I think there's something wrong with a given. All right, let me change the given. The value of x, or x should be approaching to infinity. Oh, okay, there's something wrong with a given, sorry. So this must be infinity, all right? Okay, wait a minute. So let's change the given. It should be infinity. Infinity, 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 and infinity. Okay, so the limit of 0 as x approaches infinity is still 0. So this is infinity. Okay, and here, so this is wrong. Okay, let's solve for the limit of this. The limit 1 over 3 minus 2x as x approaches infinity. So this becomes, oh, what? So this becomes 3 minus infinity, right? And 3 minus infinity is just equal to negative infinity. And of course, as the value of the, okay, let's express it in this manner, 1 over infinity. Okay, so as we express this in this form, 1 over infinity is 0, and negative 0 is just equal to 0, right? So therefore, this is equal to 0, and this is equal to 0. So the limit of cosine square of 2x over 3 minus 2x is sandwiched by the two values 0 and 0, which means that this is equal to 0. Okay, so now we have already identified the limit of the given function as x approaches infinity. All right, so there's something wrong with the given, okay, value. Okay, so I hope we got the same answer, even if the value of x here, or as the limit of x approaches 0 has is not actually 0 but infinity. Okay, but I hope also that you got our answer, you got the same answer as mine, like 0 to 1/3. Okay, so if it's 1/3, then we cannot find the limit of cosine square uh, of 2x over 3 minus 2x, since there is a big gap between 0 and 1/3, right? We cannot find any. There are infinite numbers or values that we can find from 0 to 1/3. So therefore, there's no specific value for the limit of the given problem. All right. So for now, it's pending. Okay. And we can say that it doesn't exist because there are infinite numbers of values of the limits that we can find. That's from 0 to 1/3. Okay. But again, once we change the value 0 to infinity, our answer becomes 0. Okay, so let's work on number 6. Okay, let's try number 6. How do we solve number 6 here? Again, let's work on the trigonometric function cosine for x, since we know that cosine has a specific range, okay, a smaller range from -1 to 1. Okay, so here, let's write it down. So that's cosine for x Okay, again, the range of cosine function is from 1 to -1, or from -1 to 1. Okay, oh, here we go. Wait a second. Okay, so we're going to express the middle term in terms of this given function. So first, we need to multiply both sides by negatives. And again, what we can do is still the same. We can express it in this manner for x. All right, so I did a shortcut. This becomes positive, this becomes greater than or equal, and greater than or equal, this becomes negative, and I switch the position of the negative and positive. So here we have, okay? All right, so next is there must be a 2x squared, 2x squared minus cosine 4x. So we need to add both sides by 2x squared. So 2x squared minus 1 less than or equal to 2x squared minus cosine of 4x less than or equal to 2x squared minus 1. And it should be divided by x squared. So x squared minus 1, so x squared minus 1 and x squared minus 1. All right. And we need to take the limits of all of the terms. So let's take the limit as x approaches infinity. Okay, so we have the limit of, let's use the next slide. So the limit of 2x squared minus 1 over x squared minus 1 as x approaches positive infinity is less than or equal to the limit of, I'm just copying the previous given, this one, okay? So this is 2x squared minus cosine of 4x all over x squared minus 1 as x approaches positive infinity is less than or equal to the limit of 2x squared plus 1 all over x squared minus 1 as x approaches positive infinity. Okay, here we go. So let's solve the limit. All right, the limit on both sides, the left-hand side and the right-hand side. So let's start with this. Let's start with the left-hand side and let's use another color. Let's use blue. Okay, so let's get the limit of 2x squared minus 1 over x squared minus 1 as x approaches positive infinity. Now, how do we solve this? To solve this, we can divide both numerator and denominator by x squared, right? So that's the limit of 2 minus 1 over x squared. I am now simplifying the given expression. 1 minus 1 over x squared as x approaches positive infinity. Okay? And let's take the limits of all the terms. So we have 2. The limit of 1 over x squared as x approaches infinity is 0 because the denominator is approaching infinity. And this is 1 and this one is 0 as well. So this becomes 2. All right, and we have already found the limit of the left-hand side. So we need to find the limit of this right-hand side. Okay, and let's move on to the next. Okay, to the next problem. The next solution. So let's cross this out first. And, sorry, let's use red. Okay, let's use red for the right-hand side. Okay, the right-hand side is this, 2x squared. So let's work on that. So the limit of 2x squared plus 1 over x squared minus 1 as x approaches infinity. Again, we're working on the right-hand side of the given inequality here. 2x squared plus 1 all over x squared minus 1. Here we go, all right? So how do we solve the limit of this function? Same thing with the left-hand side. We can divide both sides by, oh, what happened? Let me erase. We can divide both sides by x squared, right? Oh, here we go. So that's the limit of 2 plus 1 over x all over 1 minus 1 over x squared. Oh, this is square. Okay, since we're dividing both sides, numerator and denominator by x squared, and as x approaches infinity. And let's take the limit turn by turn. What's the limit of 2 as x approaches infinity? This is 2. This is 0 over 1 minus 0 is equal to 2. Now let's go back. So we got the value here is equal to 2. And the value on the left-hand side is equal to 2. Right? This is equal to, sorry. What happened to the pen? Okay, so the value on the, what on the left-hand side is equal to 2 as well. So the two values are equal. Therefore, this expression is sandwiched by the values 2 and 2, which means that since there are no any other values between 2 and 2, which is just 2, therefore the limit here is equal to 2. That's why the answer, or the once we evaluated this function, the answer is equal to 2. Okay, so that's how we solve limits using Squeeze Theorem or Sandwich Theorem. All right, and I hope we got the same answer. And again, let's work on number 7. Problem number 7. Okay, again, try to work on this by yourself. Okay, and once you're done, you can play the video again. And let's see if we will get the same answer, all right, and the same solution. So, oh, the problem here is the limit of x squared times e raised to sine of 1 over x as x approaches 0. Okay, this problem is quite different from the rest because the function sine is already, or it's expressed as an exponent, diba? Okay, so however, for us to use the Squeeze theorem, we will be doing the same thing. We're going to consider the sine of 1 over x. And we know that sine of 1 over x is less than 1, but greater than -1, as always. Okay? And again, same thing. We need to express the middle term of inequality to be e raised to sine of 1 over x. So how do we do that? We raise everything, okay? I mean, we place the e as the base, and all these terms are the exponents. So e raised to -1 is less than or equal to e raised to sine x less than or equal to e raised to 1. And the inequality still be preserved. Why? Because, of course, e is a number more than 1, right? Okay, so e is equal to 2.17, I think, blah, blah. Since it's more than 1, therefore, any number raised, 2 raised to -1 is smaller than the numbers when e is raised by these terms, okay? So we have, this is 1 over e is less than or equal to e raised to sine of 1 over x. Oh, I use green and e, right? Okay, let's use white, sorry. Okay, so we have already expressed the middle term to be the same as the given problem, but we lack x squared. So which means that we need to multiply all of the terms by x squared. Okay, so we have, let's write it down here. So we have x squared over e is less than or equal to x squared sine, sorry, e, this one is supposed to be e raised to sine 1 over x. Sorry. Oh, let me. So this is less than or equal to e. All right. And we have already successfully, expressed the middle term, same as the given problem. So let's take the limit. So the limit of x squared over e as x approaches 0 is less than or equal to the limit of x squared e raised to sine 1 over x, okay, as x approaches 0, less than or equal to limit of e, right? Sorry, yeah, x squared e as x approaches 0. Oh, I forgot the x squared here. Okay, so let's take the limit on each side. So let's use red for the left-hand side. Okay, so let's take the limit. What is the limit of x squared as x approaches 0? Or what is the limit of x squared over e as x approaches 0? The x here becomes 0. So 0 over 0 is 0, right? Sorry. Let's take the limit one at a time. Okay, so x squared over e as x approaches 0. So what is the limit of x squared as x approaches 0? That's 0 over e is equal to 0. So therefore, the value here is 0. Now let's take the limit on the right-hand side of the given inequality. So let's use blue. Okay, and what's the limit of x squared times e as x approaches 0? What is the limit of x squared as approaches 0? That's 0 times, what's the limit of e as x approaches 0? That's e. And 0 times e is equal to 0. So therefore, we have already found that, okay, we have found that 0 is less than or equal to the limit of x squared e sine of 1 over x is less than, as x approaches 0, is less than or equal to 0. So which means, again, since the expression or the function, the limit of the function given is sandwiched by 0 and 0, therefore, the limit of this function is 0 using Squeeze Theorem or Sandwich Theorem. Okay? And I hope we got the same answer. And let's work on the last item in the problem. So the limit of 5x squared minus sine of 3x all over x squared plus 10 as x approaches negative infinity. And let's try working on this problem, okay? And again, let's work on sine 3x. Why? Because we have already defined the specific range of the sine function, which is from -1 to 1. So we have sine 3x is less than or equal to 1, but greater than or equal to -1. All right, so again, we need to express the middle term in terms of the given problem. So we need to express it in this form. So this becomes 1 is less than or equal to negative sine. Oh, sorry. This must be, yeah, what I can do is I can put this negative and this is equal to 1 to make a shortcut. All right, but this one is negative. Again, I can multiply both sides by negative and this becomes positive, this becomes negative, and the inequalities will be reversed. Okay, this becomes greater than or equal to, greater than or equal to. So, but I can rearrange it in this manner, okay, such that the negative one is on the left and the positive one is on the right. Okay, on the right side of negative sign. And sine and 3x. Here we go. Okay, so we have already found negative sine 3x. So we need 5x squared. So we need to add 5x squared in all of the terms 5x squared minus 1 less than or equal to 5x squared minus sine 3x less than or equal to 5x squared plus 1. And here we go. We have already found the numerator, and we need to divide this by x squared plus 10. So the other two sides should also be divided by x squared plus 10. X squared plus 10. Okay, and we're now ready to take the limits of the terms. So we can say, okay, let's work on the next slide. So that's the limit of 5x squared minus 1 all over x squared minus 10. Is that correct? Minus 1, oh, plus 10. As x approaches negative infinity is less than or equal to the limit of 5x squared minus sine 3x all over x squared plus 10 as x approaches negative infinity is less than or equal to the limit of 5x squared plus 1 all over x squared plus 10 as x approaches negative infinity. Okay, so we have already expressed the given compound inequality in terms of limits, their limits. So we need to take the limits on each side. All right, if it's possible, if we could find the limits of all of the terms, then we can. But since the middle term of the compound inequality is quite hard to evaluate its limits, then let's take the limits on both sides and let's see if we can find something. All right, so we have, let's work on the limits on the left hand side first. So that's limit of 5x squared minus 1 over x squared plus 10 as x approaches negative infinity is equal to. Okay, now again, since the powers of the variable x are equal, then we know how to deal with them. So we can divide both numerator and denominator by x squared. So this becomes 5 minus 1 over x squared all over 1 plus 10 over x squared as x approaches negative infinity. Okay, now since this is negative infinity, we need to be very careful. However, since the variables x are with even power, okay, so that's 2 and 2. Therefore, the negative infinity will just be positive infinity. So that's the limit of 5 is 5, of course, and the limit of 1 over x squared is still 1 over infinity. That's 0, right? And the limit of 1 is 1 plus, what's the limit of 10 over x squared as x approaches negative infinity? That's 10 over positive infinity. All right, so that's 0. So this becomes 5. So therefore, the limit on the left-hand side is 5. So let's write it down here. Now let's work on the limit on the right-hand side. So let's work on that on the next slide. So we have, oh, sorry. So let's use blue here. So that's the limit of 5x squared plus 1 all over x squared plus 10 as x approaches negative infinity. Okay, so let's evaluate the limit. We're going to do the same thing, okay? We're going to divide both numerator and denominator by x squared. So this becomes 5 plus 1 over x squared all over 1 plus 10 over x squared as x approaches negative infinity. Let me check. All right, here we go. So let's evaluate the limits. The limit of 5 is 5 the limit of 1 over x squared as x approaches negative infinity, it's 0, it's 1, and this one is 0, and this is equal to 5. So the limit here is equal to 5. And if we compare the given function, this function, I mean, the limit of the given function is sandwiched or squeezed between the values 5 and 5, which means that there are no other values between 5 and 5 except 5. So which means, all right, it implies that the limit of this problem is equal to 5. Okay, so that's the answer. And I hope we got the same answer again, okay? And I hope everything is clear. And if you have some questions or comments regarding the solution, please do comment under the video. Thank you.